Project is entitled Gesture Recognition Using Real-Time EMG. The aim of this project is to use EMG signals recorded from the surface of forearm muscles transmitted wirelessly for operating various applications in a PC. The objectives are of three: to create a prototype which uses surface EMG signals in real time, to obtain the movement of slides in a PowerPoint presentation using Zigbee, and to obtain the operation of a virtual keyboard in LabVIEW, again using Zigbee protocol. The proposed system has surface EMG sensors to detect the signals from the forearm, transfer of these EMG signals to a laptop, the change of slides through wireless transmission using Zigbee, and in LabVIEW, the application of a virtual keyboard. The block diagram has both the transmitting section as well as the receiving section. At the transmitting section, you can see two EMG sensors, one connected to the wrist and the other connected to the forearm, an ADC, a power supply, LCD display, MUART, and Zigbee, all of which are interfaced with a microcontroller. At the receiving section, we have Zigbee again, MUART, and the PC. The hardware requirements include the EMG sensors, the ADC, MUART, Zigbee module, LCD, microcontroller, and power supply, and the software requirements are Embedded C, Visual Basic, and LabVIEW. The methodology shows the flowchart where first you have the surface electrodes that record the EMG signals from the forearm muscles. The ADC then converts these analog EMG signals into the digital type. The microcontroller receives these digital signals from the ADC, and the MUART receives these signals from the microcontroller for serial communication. The Zigbee transmits the signal received wirelessly to the receiving section, and at the receiving section it is received and sent into a second MUART that senses the display on a PC. The working shows that there is muscle activity present when a voltage is developed in the muscle, which is sensed by the sensor. For the opening and closing of fingers, there is one voltage, and for the movement of forearm, you have another voltage. These voltages are first stored in the unit and serve as a database. During the PowerPoint presentation, when these voltages are matched, there will be a movement of slide either forward or backward. The same applies for the virtual keyboard. This shows the transmitting section with all the components labeled. This is the receiving section, which is connected to a laptop. The electrodes are placed like this on the arm for movement. The voltages are as seen, which are already stored in the database for match. This shows the application of the PowerPoint presentation in Visual Basic. The movement of the wrist starts the PowerPoint presentation, and the slow upward action causes the forward movement of slides. As you can see, it's going from 1 to 3. The fast backward upward motion causes the slides to move to the previous type, which goes from slide 4, 3, 2, and 1. The virtual keyboard application is in LabVIEW and has row selection, display of the selected key, and ending the application when the message is typed. These follow the same motions of the hand. This is the virtual keyboard as seen in LabVIEW, which has the alphabets and the message display, and this shows the same motions of the hand, which the upward wrist action causes the toggling of the LEDs between the keys. The upward action of the hand causes the display of the selected alphabet onto the display space. When the arm is moved fast and on reaching the done key, it closes the application. The future scope shows a sensor array that can be created to pick up minute muscle activity. A wide range of applications can be programmed like volume control, document reader, media player, etc.